find me doing it's hard to try to dig your way to the central steps. Pieces, you just get the grants. All right, welcome everyone. I'm glad to see a number of faces here in the room with us. We've got quite a crew online today as well. All right. Well, thank you all for being here. I'm Sarah Brewer. I direct the education program at Accords, and I want to welcome you all today to our seminar program. For those of you who are new to Accords or need a little refresher, Accords is supported by the University of Colorado School of Medicine and Children's Hospital Colorado. It's a unique one-stop shop for faculty to conduct pragmatic research, receive various types of services and supports for grants and projects, along with incredible mentorship training and education in health services research. I want to specifically highlight our strong methodological cores, and particularly our biostats and analytic core, who has partnered on this particular series. So thank you. A few of our other upcoming events. So we have we have two more actually in this series on statistical methods for pragmatic research. So you'll see April 15th and May 20th, we have special external guests joining us, Dr. Michael Matheny and Dr. Keith Goldfeld. So I hope you will also join us for those as we wrap up this series in the spring. We also have on April 3rd, the last in our ethics, challenges, and messy decisions in shared decision making. And we'll be hearing from Dr. Chris Knopke and Laura Shearer. And then on April 26th in this room, for those of you who are here in person, we'll be having our Community Engagement Forum final event of the year, which will be our Community Engagement Showcase. And we're really excited to have a number of community partners joining us here on campus. And then, if you have not yet, I highly recommend going to coppercon.com and registering for this year's Colorado Pragmatic Research in Health Conference, and that'll be June 5th and 6th. It's a virtual conference. Registration information is there on the website. So we hope to see you there. Before I introduce our speakers today, just a couple housekeeping items. We will have time for a question and answer at the end of the hour. If you are online, please go ahead and use the chat and the Q&A. We will be monitoring that for that Q&A session. For those of you in the room, you'll have a chance to raise your hand and we'll come around. And then second, we ask that you all take a couple minutes to complete our evaluation. If you're here in the room, there are paper versions in the back, and if you are on Zoom, it'll pop up when you log out, but we'll also share it in the chat right before, during the Q&A time. All right, so today's seminar is part of our Statistical Methods in Pragmatic Research. It's the 7th of 9 in this series, and we welcome Drs. Ryan Peterson and Katie Colborn today. Ryan Peterson is an assistant professor of biostatistics and informatics at the Colorado School of Public Health. He's the director of the Pulmonary Translational Biostatistics and Bioinformatics Core, and is a member of the Center for Innovative Design and Analysis at CU Anschutz. His methodological research interests include model selection, model transparency and interpretability, methods for missing data, statistical computation, data pre-processing, and post-selection inference. Additionally, he writes about best practices for statistical collaboration and training the next generation of statistical practitioners. Welcome. And Dr. Katie Colborn is associate professor in the Division of Healthcare Policy and Research in the Department of Medicine, and she directs the Biostatistics and Analytics Core at Accords. She also holds secondary appointments in the Department of Biostatistics and Informatics at the Colorado School of Public Health, and co-directs the Data Informatics and Statistics Core of the Palliative Care Research Cooperative Group. She's received extramural funding for her own research and has collaborated on numerous extramural research grants. Her research interests include design and analysis of randomized controlled trials and cluster randomized trials, analysis of electronic health record data, and health services and outcomes research. Welcome, Drs. Peterson and Colborn.
All right. Thank you, everybody, for coming in person and online. So yeah, I hope you're able to get out what you hoped to get out of today's talk. We're going to be talking about pragmatic statistical learning from data to interpretable insights. And I guess to start off, I think when I graduated from grad school in biostatistics, the pragmatic, practical challenges involved with data analysis were completely foreign to me still, right? They don't do a great job of training, I feel like, in a lot of programs, what it's like to deal with real data sets. For instance, one of my professors in grad school told me, the best missing data strategy is to not have any, which I guess is true, but it's not that helpful when you have a data set in front of you that has lots of complicated missingness. So today we're going to really go through kind of the perils of real data and the challenges that accompany real world data. We'll go through some case studies, some interpretation, or some thoughts on interpretation, and also what I have come to believe are really, really good methods for pragmatic statistical learning methods. And then I'll start by doing a little bit of that discussion, and then Katie's gonna come up about 2/3 of the way through, ideally, to talk about her Aspen project and how that kind of relates to what the rest of this talk is. So yeah, as the outline, the plot that you see here on the right is kind of the whole data gathering and analysis process from start to finish. It's a little bit small here, but you can see that there's a lot of steps involved. And I think the perils of real data come when all of these steps kind of are not something that you can perfectly design in an ideal world. So we'll specifically touch on machine learning, right? Because that's the title of today's talk, and we'll talk about how different methods work better or worse with respect to what you need for pragmatic research. And then we'll go through some case studies. I'll talk, as I said, about interpretability, and we're going to spend a little extra time on penalized regression because that's, in my opinion, a very pragmatic choice. So just to bolster what I just said about classroom versus real data sets, in the classroom, the statistician uses data sets that are supposed to showcase how statistical methods work, right? So p-values work well in these types of data sets, that you can kind of understand those things pretty well. They tend to be small data sets. They tend to be complete data sets with no missingness, or at least filtered to complete cases. They tend to be very well documented, so you know exactly what each column in your data set is, how it was measured, what time it was taken, et cetera. And they also tend to be one row per independent observation. So as you can imagine, real data sets contrast all of these quite a bit, right? Real data sets are extremely large, frequently missing in complex ways. They've usually got a complicated structure, meaning that they've got repeated measurements, and this can look like multiple measures over like regularly spaced intervals, or it can be like, when did this person come into the hospital? That's when they actually show up in your data set. Other ways that you can have complicated missingness, there's sometimes structural missingness, like if you're measuring something like 6-minute walk distance, right? Well, what happens if 30% of your patients actually die before they get that measured? Is that really missing? Totally random? Not really. You can't just treat that as missing. So there's difficult considerations at play for that. Also, real data sets actually, even if they're really, really big, they're not easily generalizable, because one EHR system might actually look quite a bit different in terms of the practices, collection process, et cetera. And not to mention that the population itself is probably different in different EHR systems. So lots of challenges here that we're going to touch on today. Some extra considerations for big data sets, because most EHR, or there's lots of different types of big data sets out there, and there's new considerations for them that have to be considered. So one, you often can't work on a regular desktop to handle this type of data. Often you want to use big data sets for causal questions, but because of the problems we just mentioned in terms of generalizability, that can be very difficult. So the traditional methods that you learn about in statistics introduction classes, like regression or even like chi-squared tests, that kind of stuff, they tend to fall victim to bias in these cases, because those methods are all developed to help handle variance problems related to like precision. So for 200 patients, how precise can you estimate one treatment being better than another? But the question of like, well, for 200,000 patients, that question gets muddied because you can usually be very, very precise about the answer to a question about what works and what doesn't. But precision is different than unbiasedness. So you might very precisely be answering a question that actually isn't generalizable at all. So further, big data sets come in a variety of shapes and sizes. So some big data sets are really, really tall, meaning that there's a lot of observations on a relatively small set of features. They might be extremely wide with many, many features on a relatively small set of observations. They might be high throughput or functional or time series or some combination of all of these things. We'll talk a little bit more here on this slide about the difference and why it matters. So a tall data set, as you can see here, is one where N is really big relative to P. And so N here is the number of observations, number of subjects maybe. It's common to see this type of data if the data collection is cheap relative to the value proposition. So advertising, insurance, that type of data tends to be tall rather than wide. This is really uncommon in typical randomized controlled clinical trials because that data is very expensive to obtain, right? And so it's just very uncommon to see millions of observations. I don't know, maybe there is a trial out there with millions of observations, but I tend to doubt that. Like a randomized controlled double-blind trial. So high dimensional data, on the other hand, refer to wide data sets with extremely large number of features P. So this is common if you obtain many features of a single observation for pretty cheap. So things like omics related analyses where you run a panel or any sort of analysis like that, you're going to get many, many features on the same observation. And so that tends to lead to these wide data sets. And as you can imagine, if you have both high N and high P problems, like wearables or Google Trends or images, there's additional complexities that arise for those as well. Just to summarize the issues that relate to this and why I'm bringing up this distinction, when you have the high sample size, you get very stable, precise insights, and you need to be worried about bias, not variance. There tends to be this issue of diminishing returns where it might not be worth it to collect 100,000 more individuals, or it might not be worth it to include all of the possible years of your study if that's going to lead to other practical challenges with respect to the data or the generalizability. I will say in this high sample size problem, black box algorithms, which we'll touch on in a second, tend to perform better. They can predict better because those algorithms are known as data hungry. And this is the type of food that those eat, I guess. So on the other hand, high dimensional tend to produce unstable insights or imprecise insights. And so you have to be a little bit worried about whether your conclusion from a study with one of these is going to be replicable. Instead of bias being of primary concern, usually you need to worry about multiplicity. So you're looking at maybe tens of thousands of different variables on maybe under 100 subjects. And so it's really hard to adjust for multiplicity in that setting. Lots of people have worked on that problem. Another one is that causal effects are difficult to disentangle from especially correlated features. So this is what's called the Rashomon effect. It means that there's a lot of potential models that look very, very similar, and they all tell slightly different versions of the true story about what is generating the data. We'll talk about that in a little bit. So what do you do when you have both a high sample size and a high dimensional problem? Again, it's not always clear, it's going to depend, but I personally think an interdisciplinary approach is best in these situations, and it's usually important to include the ones I've listed here, including clinicians, informaticians, data scientists, biostatisticians, and many, many more. The same goes for very complicated data structures. Okay, so that's kind of background on some of the issues that we deal with. So now we'll get into some of the specific considerations of machine learning. And going back to that plot I showed earlier, so data mining or machine learning, those are kind of synonyms. They tend to fall into this like third phase of this process. So they're usually performed actually after a good amount of other stuff is done to the data to make it look cleaner. However, since this is a talk on pragmatic issues that relate to real data, we kind of have to tackle all of them at once. And so I will kind of talk about how the other phases relate here. One key distinction is that supervised learning and unsupervised learning have different objectives. Supervised learning is using information to predict something, some kind of outcome. Usually in biostats, it's some sort of health outcome like time to death or general health measures, outcome measures. Unsupervised learning, on the other hand, is using information to identify subgroups of people. We'll give you some examples of that in a second. There's some other learning types we're not going to focus on here, like recommendation systems, anomaly detection. But starting with supervised learning, again, the goal is to take your training set with some covariates, X, we'll call it, an outcome Y, and we'll build a model to predict Y given those covariates. In the learning process, we usually do this process called validation. Sometimes we use cross-validation. Sometimes we have a training set and a test set, and that's how we do validation. But all that is doing is we're taking a new X that wasn't in the training data, and we're predicting Y for that new observation. So supervised learning is kind of a more expansive way of describing just general regression methods that we teach in statistical courses. So regression is a pretty simple supervised learning method. Logistic regression is a similar one. These methods are what I call transparent and interpretable, because they allow inference on how Y changes with respect to these covariates, or how Y is impacted potentially by these covariates X. I didn't mention this on the slide, I guess, but if your outcome is categorical versus continuous, you do have a little bit of differences in terms of whether you're going to use a different metric for validation. You can use like the area under the receiver operator curve for categorical outcomes. I think, Katie, you're going to use that in one of your slides. But for continuous outcomes or survival outcomes, there's the same type of thing applies. The thing that does change is what type of validation you do, what specific metric you use. So these fancier machine learning tools, I'm calling fancier because they're newer, I guess. But they include random forests, they include super learners, k-nearest neighbors, support vector machines, neural networks are, I'm sure many of you have heard a lot about those in the news because of the large language models that are out. These are deep neural networks. So these fancier tools actually do a really good job in these data hungry ways. So if they have a lot of data, they can do really well. The issue that you run into in pragmatic research is like, well, what do you do if you get this model? How do you actually interpret the results if like the predictions are good? Sometimes you can explain them using some even fancier kind of explainability and machine learning tools. But even in those cases, they're not really interpretable in the same way because you can't make inferences on how Y changes with respect to X. And we'll talk about that in a little bit as well. So for those reasons, these are called black box methods. So for unsupervised machine learning, again, there's no outcome of interest here. Just a couple key ways to use unsupervised machine learning that are very, very important in pragmatic research is dimension reduction. So this is going from a high number of variables to a low number of variables. Usually it's with respect to your covariates, but not always. And this is done without the consideration of an outcome. So you might find that a bunch of your predictor variables are super highly correlated with one another, and you could say, okay, well, we're gonna only look at one of these because it's gonna be hard to disentangle the inferences with respect to these three. Another type of unsupervised ML is like on the top right here, you just have three sets of points in 2D space and you say, okay, well, this looks like three clusters. That's unsupervised machine learning as well. Maybe more interesting, this is from a paper that used weight loss trajectory clustering, which is an unsupervised method that clusters participants into 4 different classes, I guess, or clusters of people with different amounts of weight gain or loss throughout the course of this study. The point that I want to take away from this is that most pragmatic research actually ends up a hybrid of both unsupervised and supervised methods. One example of this is fee codes. Who here is familiar with fee codes? I can't survey, I guess, the Zoom people. It's not, okay, not many. So I'll just describe these fee codes, which I know Katie and Laura Wiley here have done a lot of work with. Fee codes are an attempt to go from about 70,000 ICD codes all the way down to about 1,500 fee codes. And they're attempting to get at a classification of a particular disease type. So here you can see the ICD-10 codes on the left here and kind of their description. A lot of these ICD-10 codes are too precise. You don't need 70,000 ways of coding diseases for most pragmatic research. You just need to know that all of these, in this case, refer to some sort of post-operative infection. So that's an unsupervised learning type of method because we're going from 70,000 columns in your data set representing whether an ICD code or not is seen for a particular patient to about 1,500. Huge dimension reduction there. And it's totally usually irrespective of the outcome at hand. Another example of this is comorbidity scores. So Charlson comorbidities, Elixhauser comorbidity scores. These are methods that have been developed to, again, go from this really big space of ICD codes down to a set of meaningful like aggregates of those. That's another example of how unsupervised learning can really help you reduce your dimension from 70,000 to something that's much less. Yeah. Okay, so getting again at this idea of ML and pragmatic research. So what is needed? We've gone over some of these common issues with pragmatic data. So sometimes they're extremely large, often they're missing data, it's complex structure, not easily generalizable. I didn't, I guess, specifically touch on the fact that there's diverse stakeholders involved most of the time, but this is another consideration. And there's ethical considerations as well with respect to this. These data. They also tend to be noisy, which means lower signal. It's not as simple as running an experiment in the lab most of the time, right? You're not going to see huge effect sizes typically. There's probably many more pragmatic data common issues that I'm not touching on. So that's my disclaimer there. But I'm going to kind of translate all of these into desired properties for pragmatic machine learning methods. So for extremely large big data, we're going to need a method that's both scalable in P, the number of features or predictors, and N, the number of independent observations. Two, because we're going to expect missing data, we want a method that's going to expect and respect missing data in as much as possible. Three, we want to respect the data structure and dependence. And four, we want human interpretable conclusions that are then able to be validated and generalized potentially to other populations. For the diverse stakeholders and ethical considerations, we're going to want methods that are more transparent and relevant. We'll want methods that work in low signal settings, et cetera, et cetera. Okay, I'm going to touch briefly on privacy. And with big data sets like this, the one key question here is privacy of individuals maintained with big data? Because there is this trade-off between privacy and variety of data. Is it possible, for instance, to de-identify genomic data? That's like a big question, or imaging data. So any sort of high dimensional data is arguably identifiable to the right person. Is it possible to de-identify location data? I mean, if you saw my exact location throughout the day, you would know who I was without any doubt, right? So how do you identify that? This was particularly relevant during the pandemic when they were tracking, COVID. So you can probably de-identify these, but is it without losing very, very important vital information for your study? These are important things that come out here. Obviously, access is an important thing as well. There's a lot of further reading here. I don't have any great answers for any of these questions. I'm more just saying that these are issues that really need to be addressed in pragmatic research with this type of data. And just to make my point a little bit, I actually typed into one of the AI generator black box methods, what does privacy look like? This is a couple of years ago before the big ones came out. And this is the image that I got from AI for what does privacy look like, which actually made me very nervous because that doesn't look like a private situation at all. So just something to think about. That's kind of scary and fun at the same time, I guess. Okay, additional ethical concerns. It's worth bringing up specifics with regards to the bias that I mentioned earlier. So selection and sampling bias are typically the ones that we worry most about. And again, researchers may very precisely answer the wrong question when they use real data sets. When they do this, these biased data sets have very limited generalizability, even with really, really big samples. So for one example, there was a study in Boston in 2013 that detected potholes using smartphone accelerometer data. In 2013, not everyone owned cell phones, or smartphones rather. And so who do you think got their potholes fixed out of this policy? Yeah, exactly. Wealthier neighborhoods got their potholes fixed. And this kind of, oh yeah, I guess I have, well, this kind of leads to another issue, which is algorithmic bias. So your algorithm, your learning algorithm, whatever it is, it's going to work best on the data that you trained it on. And it's going to work worst on data that wasn't in the training set. So algorithmic bias comes into play when the people who are getting predicted about aren't represented in the data, and therefore the predictions aren't as good as you would hope. And that can lead to pretty big problems, both in terms of like predictive policing. This is a big issue, but also even here at the university, we had Proctorio as, is anyone familiar with Proctorio? We had a contract with them, and during the pandemic, they said, you guys should use Proctorio to automatically detect whether students are cheating over Zoom. Well, guess who was in the training data, and guess who was flagged more for cheating based on skin pigmentation, things like that, because they weren't in the actual, so this was a problem. A lot of us didn't use Proctorio because we kind of recognized it as algorithmic bias at the time. But it's worth considering, like, the limited generalizability of some of these methods is very, very limiting potentially in practice. As far as transparency, so how can we trust in black box ML when we really don't understand how they work? This is a hot topic now with the LLMs, that we don't understand how they work either. They've got what people are calling emerging properties, and we're learning more about them every day. Maybe that's an okay model, but it's not a very scientific model, which is to understand first and then to move forward. Also, who are the stakeholders? Who is accountable for ML systems ultimately? I've gotten a lot of mixed answers for this question. I have asked it to a lot of people. My best argument is that the patient, for health outcomes, the patient is ultimately responsible for ML systems working for or against them, because they're the ones who will eventually either benefit or be harmed by them. Okay. So what this slide goes into is different types of methods, ML methods specifically, that you might apply in pragmatic research. So here I've listed some of the common ones that we just touched on: neural networks, random forests, regression, and then penalized regression. And this is my way of saying that, like, regression and penalized regression do give you these things that aren't given to you by black box methods. So things like human interpretable conclusions, transparency, relevance, and they work in very noisy settings. That's not true of the neural networks or random forests. I've added a check here for what the methods that I think do extra well in different settings as well here. But penalized regression really checks all of these boxes. And that's, for that reason, I think it's a really great prospect for machine learning and pragmatic research. I have some additional resources here. I'm not going to go through them in depth, but I think the slides will be shared, so feel free to go through those. And I've got a couple case studies. I'm a little bit low on time, so I'm only going to go through one of them. But administrative data is a commonly observed source of data for pragmatic research, and it's lots of data that's collected routinely by organizations, including financial data, claims, billing, in addition to EHR data. And the reason this is pragmatic is that the data is not intended for research. It's intended for other purposes, right? We're repurposing it to do research. So this allows for extremely large sample sizes, high N. situations, and it's typically very cheap data or easy to acquire it. Tends to be well documented, facilitating data management, but it's still kind of hard because the data is usually massive. It's very, very important to consider the many possible sources of bias here. So some examples that I've worked with: Medicare, Medicaid data, Premier data, census data, NHANES data, and HCUP data. All of these are sources of big administrative data. And I'll just go through one example that used HCUP data in the National Readmission Database, which is a set of all, well, it's a big sample of hospitals in the US and tracking if patients come in, do they get readmitted, essentially. And we get all sorts of billing data on those patients. And we were interested in this question of like, are surgical site infections after total knee or total hip arthroplasty, are these seasonal? Because if so, they're devastating to patients. A lot of surgeons really, really care about getting their SSI rates down as far as possible. And so this was interesting to find out. And we were able to analyze over 760,000 procedures over 2 years. And we did in fact find that the SSI rate was higher in June versus December. So that was an interesting finding, quite a bit higher, in fact, 24% higher. And we used kind of a novel way to do the seasonality estimation here. We've done similar things with cellulitis as well. This is one I'm going to skip, but it has a lot more data. And we were able to show that cellulitis also has this kind of higher in the summer seasonality kind of thing, just using this administrative data. Okay, so electronic health records are a little bit of a different type of thing, because they're going to usually include both unstructured stuff like clinic notes, medications, labs, as well as structured stuff like the billing codes and that kind of stuff. So our campus has a huge electronic health record or medical record repository, lots of resources available for working with that. And I think Katie will be going through a detailed example of this in just a few minutes, so I'm going to skip this one. The last thing I wanted to mention is that registries are kind of the new frontier, I think, in pragmatic research, because they can be combined in many different ways with many different types of big data. So the All of Us is kind of an interesting study that's disease agnostic, and it's going to be collecting, or it is collecting, all sorts of data on all sorts of diseases. There's a few others here. I'm a little bit low on time, so I'm just going to get to the next one, although I will point out that several of our colleagues have been working on the UK Biobank study looking at wearable data, and they've got some really cool papers using wearable data on this really, really large cohort. This is kind of one of those really big data, both tall and wide data, because wearable data is, as you can imagine, pretty high dimensional. Okay, so on interpretability, this is something of special interest to me. So just to clarify what I mean by this, so simple or interpretable models, they tend to have parameters which can be interpreted in sentences and words. And the process by which predictions are made are mathematically tractable and understandable, right? Importantly, insights that you get that are interpretable can be confirmed and generalized to new populations. So for example, the older a child is, the larger our prediction for their forced expiratory volume, or FEV, because their lungs get bigger. And that's just a simple linear regression can tell you that. So black box, on the other hand, black box models, if they do have parameters, they can't be well understood. Think like very high order interactions that are notoriously hard to interpret, even if you just have a one order interaction. The process by which predictions be made need not be mathematically tractable. Basically what you get is you input your data and you output predictions, and there's a question mark in between that's just left blank by the researchers on purpose to say, like, let's let the machine figure out how to model this best. What this leads to, though, is that the insights you get from this are only applicable to those represented in the training data, which is kind of problematic. So there's also this interpretability of specific relationships in terms of, does X cause Y or impact Y, or does it change when X changes? These are different ways of kind of getting at associations or maybe causal associations between a variable X and an outcome Y. Typically, saying in regression, like holding confounders constant lets us get closer to a causal interpretation of like this relationship. Note that some variables should never ever be considered predictors here. So things like mediators, if they're not available at the time of prediction, if they're frequently missing, if they're, there's a whole reason not to, a set of reasons not to include certain covariates, but for the most part, once you consider all of these things, you can get to a pretty interpretable model at the end of the day with regression. So while explainability tools can help uncover some sort of importance from some of these, and can even describe functional forms between X and Y in these black box models, regression models are simpler. And penalized regression models basically still give you the same thing, which is a risk equation. In terms of inferences, in statistics, we not only ask, does X impact Y? We ask, does X impact Y significantly? That is the relationship strong enough that we can't attribute it to chance alone? And we've always used, or not always, but for a long time, we've used p-values and confidence intervals to get at this question. These tend to be well understood and interpretable, though they certainly have their issues. Unfortunately, these are really only available for regression. And this time, penalized regression doesn't help because penalized regression, you don't get p-values and confidence intervals for. So there's the first X in the notch for penalized regression here because it doesn't give you p-values. However, it's a half and half situation because, there are some options for post-selection inference after penalized regression. So knockoff filters are one version. There's things like stability selection, bootstrapping, marginal false discovery rates, selective inference. These are all cutting edge methods to help with this process of inference after penalized regression, but they all are somewhat limited in certain situations. So it's just worth knowing that, there might be a negative to using penalized regression in some cases. Also, one thing I wanted to mention is that when candidate predictors are highly correlated with each other, modern tools do become unprecise or imprecise. And I found that considering such features as substitutable can help. So for instance, BMI and waist circumference might be both candidate predictors in a model. But if you're interested in like associations between these things and your outcome, an irrelevant question to ask is BMI important conditional on waist circumference? Because you don't probably have much signal there at all, right? Those things almost always go pretty close together. The relevant question is either BMI or waist circumference important in predicting this outcome? And that is actually not answered by default in most high dimensional methods. So that's worth discussing. So with that, I think I'm going to turn it over to Katie for the Aspen.
Okay, so I'm just going to provide a real world example. Ryan and I have co-mentored some graduate students together and identified our shared appreciation for penalized regression. So we figured if we team up for this talk, we could really show the importance of the methods and also how it might be applied in a real world setting. So I am MPI on a R01 funded by AHRQ with Dr. Rob McGeed, who's a thoracic surgeon. And this project is called Automated Surveillance of Postoperative Infections, or ASPEN. And the idea is to essentially try to replace manual chart review with automated methods. And we do this by developing and validating models where we've merged gold standard outcomes data to electronic health record data. So the gold standard we're using is the American College of Surgeons National Surgical Quality Improvement Program. This is a program that's been around for at least a decade, and there's over 800 hospitals that participate. We were looking locally so that we could merge the NSQIP data set to our local EHR using a medical record number and other personal health identifiers. And we were looking at data from the EHR up to 365 days prior to an operation to 30 days after. And the idea is twofold: to identify postoperative infections of 4 different types that I'll talk about in a minute, and then also to try to get a preoperative risk of these infections in the same patients so that we could risk adjust estimated rates of complications. You can see the EHR data set for this approximately 6-year period is nearly 670,000 patients. Some of those are kind of minor operations on the same day, so we limited this to 1 operation per person per day, and that was still over 400,000 patients. The NSQIP sample being only about 30,000 of those. So really right now what we're getting is an estimate of postoperative infections in about 10% of operations that occur across 5 hospitals in the UC Health system. So we're kind of blind to a large proportion of our patients' outcomes, and that's because manual chart review is time consuming and expensive. So what we wanted to do, again, is separately estimate models for each infection type. So we had surgical site infections, sepsis or septic shock, pneumonia, and urinary tract infections. And those would be models where you would look at like patient factors, preoperative diagnoses of things that are related to a postoperative event. And then in the same patients, look at their 30-day postoperative period of time and identify factors that might help us look for complications that occurred in the data. So the objectives of the 2 sets of models were slightly different, but would be used in combination to estimate risk-adjusted rates. And Ryan talked a little bit about the different dimensions of data types, but when you're looking at electronic health record data, they're often both tall and wide. So you've got multiple observations from the same patients over time. You also have lots and lots of exposure variables. So what happens, especially when you're looking at diagnosis codes and procedure codes, is that if anyone has a particular code, that becomes a variable, and that actually now gets transposed to a column in your data set. But for a lot of people, they didn't have that diagnosis, so they're just zeros. So you end up not only with a very large data set, but a very sparse data set, meaning there's lots of zeros in your data set. And we ended up with approximately 15,000 predictors on the right-hand side of the equation for 30,000 patients. And this was after we mapped all of the ICD codes to fee codes. So very kind of messy data set, but we divided this data set, it was of 30,000 patients, into training and test sets. So just a quick note on that is anytime you're developing models, especially in supervised learning settings, you want to hold out some data that you're going to test on, because it's very easy to overfit to a particular data set when you're doing machine learning or even penalized regression. And the idea is to say, how well does this perform outside of the data in which I trained my models? So you want to have a larger set to train on, and we use 70% of the data to train and temporally split that. So we had 30% held out. If you want to know more about how to design your training and validation, I recommend reading the tripod guidelines from the Equator Network. That's a really good place to start in terms of understanding the hierarchy of test versus validation. A temporal split in this case was important because we thought we're developing the models in patients historically, and we want to be able to provide a prediction on a new patient that comes in tomorrow, for example. So what we did was use a penalized regression technique, which Ryan introduced us to. This technique we use is called the lasso, or least absolute shrinkage and selection operator. It basically selects variables by allowing some of their coefficients to be equal to 0, which means they drop out of the model. And then we added another layer of protection against false discoveries, essentially, called the knockoff filter. And this approach actually creates a whole bunch of knockoff counterparts, so fake variables the dimension in width of your data set becomes ×2, and every variable has a knockoff counterpart. And the idea is that each variable's coefficient has to be sufficiently larger than its knockoff counterpart in order to be selected. So you end up with slightly more parsimonious models if you add this false discovery rate correction through the knockoff to your lasso. Part of the reason we did this is because through focus groups with surgeons, we discovered that these black box algorithms just weren't really going to fly. I mean, they don't want you telling them what their surgical site infection rate is in their patients by saying you threw their data into a black box algorithm and here, trust me, here's your infection rate. They like to be able to say, oh, it makes sense that you had a diagnosis code for a surgical site infection. The patient had a positive blood culture. They had a procedure of a culture done, and they were prescribed an antibiotic. All those things are variables that we can now actually apply a coefficient to, and we had better buy-in from surgeons by taking that approach. So our models, when we fit them, again, we applied them to the test set, the 30% held out test set. Not surprisingly, the pre-op models don't perform as well as the post-op models. If you think about it, it's harder to predict something that might happen in the future than it is to look through the chart and try to find something that probably happened. So the types of variables we ended up with in our preoperative models were risk factors at the patient level that you might think about. So what type of operation are you coming in for? Is it just like a knee replacement, or did you have like a traumatic event and you are coming in with a dirty wound? And that's going to put you at much higher risk. Also, some patients come in with preoperative diagnosis of an infection, and that's called present at time of surgery, or PATOS. That happens a lot in surgical site infections and also sepsis. But other things that are maybe a little more vague are comorbidities, what's your anesthesiology class? And those are things where you might also even be misclassifying patients in terms of their exposure, because not everybody gets the diagnoses that they should for their comorbidities. So I think there's a lot more room for error in the pre-op models, whereas the post-op models, which all had an AUC above 0.9, you get really obvious results like a post-operative fee code, post-operative infection fee code, blood culture, antibiotic prescribed. Patients who have a history of urinary tract infection, more likely to have a post-operative urinary tract infection. And then we took these two sets of models and estimated what are called observed to expected event ratios, or OE ratios. And to do this, you pick a aggregation. So here we have 5 different hospitals in the UC Health system. So if we take one hospital and we say, let's sum up all of the probabilities that the event occurred using the post-op model, and we divide by the sum of all of those same patients' preoperative probabilities, then we can get a single OE ratio for that aggregation. So for hospital 1, SSI, we get that single OE ratio, and then we can use binomial estimates to get confidence intervals on that. There's a number of different ways you can do it, and we have a paper on this that hopefully some journal will accept soon. But here we show a comparison. So you can see Aspen all, that would be all operations, so 444,000 over that 6-year period. Aspen EHR NSQIP, so this would be the subset where we applied the Aspen models, but it was from the NSQIP 30,000 patients. And then we just used the NSQIP nurse manually reviewed data. So those are all actually zeros and ones in the numerator, and we used the sum of their probability of risk using NSQIP predictors in the denominator. So we wanted to compare, like, how well are our models doing for the same NSQIP patients, and also does it look similar if we scale it to all of the operations? And so within a single box, you can see the comparisons. The triangles and squares should be similar. The circles might be slightly different because it's a slightly different patient population. And we do pretty well, especially if you look at the confidence intervals. But another thing to point out here is the confidence intervals are minuscule when you can apply it to this large data set. So instead of telling surgeons that, yeah, roughly on average, you have an OE ratio of 1, which means the right number of complications for what you would expect given your patient population, but you can make a lot stronger conclusions when you're applying it to the larger data set because all of your confidence intervals don't overlap 1. Many of them actually do not overlap 1. And we found that to be meaningful. And in general, I think you need to still do manual chart review prospectively, because anytime you're developing models and historic data, you can get model drift over time. So even just your y-intercept is off. Infections might be going down over time, and so you're overestimating infections. Maybe something else in the healthcare system changed and you need to rethink the exposure variables a little bit. But these types of models can also just augment what you're doing. So now we can provide estimates at the level of the surgeon rather than just at the level of the hospital, which is the only aggregation that the ACS-NSQIP historically has really provided. So that's just an example where we applied many of the methods that Ryan introduced in our real world data set, and it seems to be well received by surgeons, at least at this point. So thanks. I think that's it. Yeah.
Thank you, guys. Do we have any questions here in the room? I didn't see any in the chat, but if you are online, you are welcome to chime in there as well. Hold on.
For the postoperative methods, how would you interpret the coefficient that goes with the diagnosis of that condition? I mean, it seems sort of, definitive, they got that. So, I mean, it seems like if you have a high OE, that could be that you're over or under diagnosing rather than having more or less complications than you think.
Yeah, I mean, for the post-op models, the odds ratio on like the fee code for postoperative infection for SSI was like 15.3.
Okay.
So essentially, if you're looking in the chart for surgical site infections, the first place you should look is in the diagnosis codes. Because if that's there, there's a pretty good chance that that patient had an infection. If you're still ambiguous, you can add the odds ratio of 2 that they also had an antibiotic prescribed 2 to 30 days after their operation. And on top of that, if they had a blood culture, you're starting to get really confident that that patient had a postoperative infection.
Did you have a way of determining postoperative infection other than the diagnosis code then?
Yeah, so if you didn't have that code, your signal was weaker, your predicted probability was weaker, but if you had, for example, any of the other, it's just a logistic regression model essentially, and you've got like 5 variables. So anyone who's got those exposures, their probability kind of varies, but it's strongest if that diagnosis was there. Now, there's of course surgeons who feel like the ACS-NSQIP data aren't super reliable. So your training data can sometimes not be definitive, but it's the best that we have, right? So the NSQIP nurse might have missed some infections too, or found some that are questionable, but you've got to kind of go with something to be the gold standard when you're doing supervised learning.
Yeah, that makes sense.
Yeah.
Okay, cool.
Any other questions here in the room? All right. Well, thank you so much, Katie and Ryan, for sharing your expertise today. I learned a lot. Thank you.